Assalamualaikum, we are from 3ZK09A. In this video, we will discuss about heat from heavy duty diesel engine. So our lecturer is Prof. Madia, IR Dr. Muhammad Rozimin bin Abdul Rahman, and our group members is ZAID ASYRAF, AHMAD KAMAL, FAZRIL AZIM, and AHMAD NABIL. So I will explain about heavy duty diesel engine and renewable energy. A heavy duty diesel engine is a type of internal combustion engine designed for use in commercial and industrial applications where high level of power, durability, and fuel efficiency are required. These engines are typically larger and more powerful than other types of diesel engines and are used in a variety of applications including truck, buses, construction equipment, and power generation. They are known for their high torque output, low emission, and long service life. For renewable energy, refers to energy sources that are replenished naturally and are considered to be sustainable, environmentally friendly, and non-polluting. Examples of renewable energy sources include solar, wind, hydro, geothermal, and biomass. Unlike non-renewable energy sources such as coal, oil, and natural gas which are finite, renewable energy sources are abundant and can be used continuously without running out. The use of renewable energy sources help to reduce greenhouse gas emission depends on finite fossil fuel and mitigate the impact of climate changes. Now we will get into our research. There is scientific agreement that human activity is the primary cause of the observed global warming since the mid-20th century. This rise in the global average temperature has several physical repercussions including warming of the atmosphere and the ocean, as well as decreasing snow and ice cover and increasing sea levels. The rise in greenhouse gas emissions in the atmosphere is linked to the warming, which is commonly measured in tons of CO2 equivalent. The relative contribution of several economic sectors to the total greenhouse gas emissions of the European Union on the left and the contribution of various transportation sectors on the right. This project focuses on the heavy-duty diesel engine contribution to the transportation industry. According to the figure, the transportation sector accounts for 33% of total greenhouse gas emissions, with heavy-duty vehicles accounting for 19% of those emissions. Therefore, reducing greenhouse gas emissions from heavy-duty vehicles has the potential to dramatically cut total greenhouse gas emissions.
Okay, so we move to the principle. Heavy duty diesel have four principles, which is organic Rankine cycle, organic flash cycle, trilateral flash cycle, and transcritical Rankine cycle. So first is organic Rankine cycle. The organic Rankine cycle provides our option for finishing the system of equation by determining the saturated vapor state at the evaporator, exit or condenser inlet, the enthalpy at the exit or inlet as the saturated vapor condition at the corresponding pressure. Alternatively, by adding a defined degree of superheating, the superheated temperature is set at the equivalent saturation temperature. This is stated in four equations, only one of which can be determined in the cycle simulation. So second is trilateral flash cycle. There is just one condition at the evaporator outlet for the trilateral flash cycle. For example, saturated liquid at the evaporator outlet. As a result, the enthalpy at the evaporator outlet is set to the saturated liquid enthalpy at the evaporator pressure. So the below is the mathematical expression for trilateral flash cycle. So next is transcritical Rankine cycle. There is no evaporation in transcritical Rankine cycle. The condition at the evaporator output cannot be adjusted. As a result, either the saturated vapor condition at the condenser inlet or the saturated vapor condition at the condenser pressure is established. Alternatively, the superheated temperature at the condenser intake is set by adding a predetermined amount of superheating to the saturation temperature at the condenser pressure. So, transcritical Rankine have two equations. So next is organic flash cycle. The enthalpy at the evaporator outlet in the organic flash cycle is adjusted to the saturated liquid enthalpy at the evaporator pressure, as in the TFC. To determine the intermediate pressure at the flash vessel, an extra equation is required. Inlet when a constant pressure ratio is employed.
So, for the existing system, this study's engine is a heavy-duty direct injection 6-cylinder inline diesel engine with a brake power output of 302 kW. The engine is two-stage turbocharged with intercooling and meets Tier 4 fineness emissions regulations for off-highways vehicles by employing cooled high pressure (EGR) and a comprehensive after-treatment system that includes a diesel oxidation catalyzed (DOC), a diesel particulate filter (DPF), and selective catalytic reduction (SCR) with urea injection. So the typical operating cycle shows how the engine spends the majority of its time at full load and medium to high speed conditions, resulting in the availability of a large amount of exhaust gas at medium high temperature, suitable for heat recovery via bottoming cycles. Condensation problems in the ORC exhaust heat exchangers. The exhaust gas thermal power is calculated with a lower cooling limit of 90 degrees Celsius and a low sulfur content diesel fuel. Temperature data for the reference engine's exhaust line are only available until the low pressure turbine outlet, not including the after treatment system. However, based on the finding of examination of some other steady state proprietary Ricardo HDDE test data in which temperatures in the after treatment are measured, it is possible to conclude that there is no temperature change throughout the after treatment system, particularly in the engine high speed and torque range considered in this study. So, modeling. In this work, two ORC architecture are considered. A simple operator of configuration to recover heat from tailpipe exhaust gas and a parallel evaporator configuration to recover heat both from exhaust and EGR gas. The engine and the main ORC component, evaporator condenser, pump and expander, can be observed, which reports both the simple cycle and the parallel cycle ORC architectures. And the two different heat sink configurations, the indirect condensation one using the engine high temperature cooling circuit and the indirect condensation 2 using a dedicated ORC lower temperature circuit.
The evaporators are placed after the after-treatment system and instead of the EGR cooler. In this preliminary study, the increased back pressure effect of the boilers on the engine is not considered. The two investigated heat sink solutions can also be observed. Indirect condensation 1, a configuration using the engine and EGR high temperature cooling circuit as heat sink for the ORC system, and indirect condensation, a configuration using a lower temperature cooling circuit with the purpose of increasing the net power output of the bottoming cycle, allowing a higher enthalpy drop in the expander. In the second case, an additional radiator is needed. The two ORC architectures are evaluated with both heatsink configurations for a total of 4 cases as reported in the figures. The coolant is a mixture of water and ethylene glycol with a 50% mass of composition for the two components. The mass flow in the IC2 case has been considered as a variable in the optimization process. The thermodynamics properties for the coolant mixture as well as the ORC working fluid are obtained from engineering equation solver internal database. So for the conclusion, the study's findings show that selecting the best solutions, particularly in vehicle applications, is always a trade-off between several factors, including ORC performance, heat rejection capabilities, and vehicle thermal management, fluid properties, safety, flammability, availability, and environmental impact, packaging and weight constraints, component selection, and performance, engine and ambient boundary condition. So that's all for us. Thank you.